The following is from Fall 2010 Math 227 Test 2. In this video I will do number 2, part D and part E. Now let's review the question. The question was, part 2, the given situation is the length of tuna processed by a cannery are normally distributed with a mean of 24.5 inches and standard deviation of 5.25 inches. Okay, now if we already defined the x earlier, the random variable of x with the length of tuna, it's normally distributed with mean 24.5 and variance 5.25 squared. Now let me copy that here. Then x is normally distributed with mean 24.5 and standard deviation 5.25, right? I make it square to get the variance. Now then the question is find the probability that the average length of 9 randomly selected tunas is between 24 inches and 25 inches. Now we are talking now here the average length of 9 tunas, right? Now notation wise that will be x bar 9. That's the random variable of the average length of 9 tunas. That will be, as we know from central limit theorem, that will be normally distributed with mean 24.5 and variance 5.25 squared over 9. In other words, the standard deviation of this x bar 9 will be 5.25 over 3. Okay, because I do the square root there. Now what they ask here is the probability that this average length of 9 randomly selected tuna is between 24 and 25. Okay, that's the one in question. Now what I will do first, I will standardize that. Now this will be longer, 24 minus 24.5 over that variance, the standard deviation 5.25 over 3 less than x bar 9 minus mu x bar 9 over sigma x bar 9 less than 25 minus 24.5 over 5.25 over 3. Oh, that's a long one. Then if I compute this, see what I did there is actually to standardize, right? Now if I compute that, it will be negative 0.29, actually negative 0.28 something, okay, less than z less than 0.29 if you compute each one of them using calculator. Now then when I use the table, let's see first the distribution. We are talking about the area in between negative 0.29 and 0.29. Okay, now when you look at your table, you will see the area to the left of 0.29 of the standard normal distribution is 0.614. Okay, that's the area to the left of 0.29. Now minus the area to the left of negative 0.29, you will see from the table that's 0.3859. Okay, now check yourself from the table, and then when I compute this, I will get 0.2284. That one you can use your calculator. Okay, now part E, find the probability that of 100 tunas more than 55 with length more than 22.4 inches. Now if you see again, that's actually very similar to part C. Let me put part C here. The difference is in part C there are only 9 tunas, right? In part E here there are 100 tunas. Okay, and then the question is not only what is the probability that only 3. Instead, the probability that in question here is what is the probability of that 100 tunas more than 55 has that kind of length. Now let's see, let's define a new random variable. Let y2 be the number of tunas having length more than 22.40 inches. Okay, now this y2, similar to part C, there is binomially distributed, but this time the parameters 100 trials, right, and the probability for each tuna to have length more than 22.40 inches is 0.6554. Now if you want to know how I get that number, take a look again on from part A. Okay, take a look on number 2A, which we did in the other video. Now then, here, if we use calculator, actually when I asked this question at that time, I have in mind that you need to use the normal approximation to binomial distribution. But here, if we don't want to use that method, normal approximation to binomial distribution, then we can use calculator. The probability that the number of tunas having length more than 22.40 inches, what we want here is to be more than 55, right? More than 55. Okay, now I need to use calculator, but when I use calculator, it is the probability less than or equal to, that's the cumulative. Okay, which I will show you later on, is cumulative. So I cannot compute this directly, but what I can do is I do 1 minus the complement, which is probability that y2 is less than equals to, if it is not more than 55, it must be at most 54. Okay, no, I think no, not 54, 55, right? It's more than 55, the complement of that is at most 55, right? Then this is 1 minus, this will be binom CDF, cumulative distribution function of 100, 0.6554, and then 55. Okay, now let's use that. Let's use calculator to show that. I'll show it here. Let me pull it up a bit so that you can see. I will do distribution, go binom CDF, not PDF. Not PDF, I use CDF. Binom CDF, the parameters are 100 for the number of trials. The probability of success on each trial is 0.6554, and we want the cumulative up to 55. Okay, I get 1 minus 0.01865. Okay, if I subtract this from 1, that equals to 0.98135. That's the probability that out of that 100 tunas, more than 55 of them will have more than 22.4 inches. Okay, now I know these questions may be complicated. You need to slow down a bit, especially part E. Okay, because we are not talking about the probability of a tuna or the average length of 9 tunas anymore. We are talking about the probability of, out of these 100 tunas, if you have 100 tunas, what is the probability that 55 of them satisfy some quality? Now that quality is the length is more than 22.40 inches. Okay, now the probability of a tuna satisfy this quality, this requirement, has been computed in part A. That's how we get that number here. Okay, now then we use that number further for to compute the probability that the number of such tunas will be more than 55. Now then suddenly this number is coming from normal distribution, right? But right now we come up to another type of distribution, binomial distribution. because we are counting the number of tunas here. Okay, that's from fall 2010, Math 227, Test 2, number 2, Part D and Part E.